Hi, everyone, and welcome to today's episode from Covalent Metrology. We're glad you're joining us as we dive into the world of thin film thickness measurements, a surprisingly nuanced and important area of material science. Next slide, please. We're joined by two of our incredible experts, Dr. Lyle Gordon, who leads our materials, chemistry, and surfaces group, and Dr. Max Junda, my apologies, Max, a senior technical staff member focused on ellipsometry and optical modeling. You'll hear from both of them today as they share their extensive knowledge on characterizing thin films. Before we get started, we'll go over a few housekeeping notes. After the session, we'll be sharing a link to the recording and slides, as well as the full Q&A summary with answers from our speakers and technical group. You can also submit questions at any time during today's talk using the Q&A tool. Just click the Q&A icon at the bottom of your Zoom screen to open it. Next slide, please. For anyone new to Covalent, welcome. Covalent is a next-gen analytical services platform and lab headquartered in the heart of Silicon Valley. We provide high-quality data and actionable insights to accelerate R&D in advanced materials and devices. In addition to our over 50-plus cloud-integrated cutting-edge tools in-house, we also partner with over a dozen global leaders in analysis instrumentation and 40 qualified service labs to offer comprehensive testing solutions through flexible business solutions. Now, to give you an idea of Covalent's range of services, we can move to the next slide. Our toolkit spans across a huge variety of techniques. Here we've captured some of our most popular techniques across different categories of analysis. We have electron microscopy and failure analysis, microscopy and proliphometry, analytical chemistry, mechanical and material property testing, as well as X-ray and optical characterization. And with that, I'll pass things over to Dr. Gordon as we dive in.
All right, thanks, Carissa. So today I'm going to be talking to you about film thickness and how you measure film thickness. So film thickness is really critical in many applications, from corrosion-resistant coatings, semiconductor devices, as well as controlling the optical and electrical properties of materials, and many more. So you need to be able to measure the thickness to optimize and control either etching or growth process, for example, as well as understanding functional materials, and then reverse engineering, where you might not know the thickness in different applications. So we're going to be talking about how do you measure thickness and how do you approach these problems. So what techniques might be applicable in different applications or different situations, some of the limitations of those techniques that you can consider when trying to decide, and we'll use a few case studies and practical examples from a few different industries that are interesting that highlight some of these differences. And then at the end, we'll open up to some questions so we can further discuss the techniques, the examples, or some projects people are working on. So thickness varies in over a really wide range from only a few angstroms, so a few number of atoms from very thin layers, all the way up to millimeters, and for like corrosion-resistant coatings, for example. And so you're going to need a pretty wide range of tools to determine the thickness accurately of coatings over this wide range. So we're going to be talking about a few different methods that rely on either direct probes of the height or optical or X-ray methods, or as well as standard cross sections. And then we'll try and provide sort of a flow chart of how we think about different methods and how we approach a problem to determine the best approach to measure it. So how do you measure and how do you decide? So there's a few questions you can ask yourself about the sample you're looking at. And we'll walk through these and with a few examples and see how we can approach these and what the best way to do it is if they meet certain criteria or if they don't. And then there's sort of a catch-all at the end where there's some methods you can use if none of these approaches will work. So what do we do if the substrate's exposed or if it's masked? This is really common if you're making the sample yourself. So there's a lot of approaches here. It's really simple. You're basically just looking at measuring the height of the film relative to the substrate. So typically this can be done with a contact like a stylus profilometer or an optical profilometer, or if you're looking at thinner films, an atomic force microscope is going to be useful. So we'll show a nice application using AFM for a thin polymer film. So in this case, a step height, basically what you're doing is measuring the height of the film relative to the substrate. So if the film is everywhere and you can't see the substrate, then you can't do this. But in many cases, if you're making the sample yourself, like you're sputtering a film, you can just mask an area of the substrate where it won't be coated and then remove that mask after to expose the substrate. In this case, this polymer film is soft and you can simply scratch it away easily without abrading the substrate, and then go ahead and, in this case, using an AFM, take the measurement, and looking at the step height of the film from the substrate, that basically gives you the thickness. So the main limitations here are if you don't want to damage or destroy your sample, you might not be able to access the substrate, and then you'll have to be able to, or you scratch off your film. And then you get some additional information here. For example, you can see on the right of the profile that you can see and measure the film roughness. And so there's some extra information here that's accessible. And this is really easy and really widely used. Many people might be familiar with doing this when they're growing films to quickly check the film thickness. All right, the next case is if your films are optically transparent. There's a lot of practical approaches here, and I'm going to hand it off to Max now to talk about how we use ellipsometry to characterize these films, and specifically for different thickness measurement.
Sure, yeah, thanks, Lyle. Ellipsometry can be used in a variety of cases. It can also, quick plug, can be used to measure films that aren't optically transparent. However, the key thing is in cases where you want to measure the thickness of films that are present, it does require optical transparency. The light needs to be able to make it into the film and get back out. So you can see really quick just on this schematic here that ellipsometry is able to access film thickness over a really wide range. It spans basically angstrom, so almost atomic layer, up to tens of microns in a practical sense. So we'll go to the next slide. And before we get going on some of the considerations for measuring thin films and some applications, I want to just give a quick background on how ellipsometry works. I will resist my urge to dive into the weeds too deeply on how ellipsometry works, and I will plug our webinar library where we have other webinars that do a much better job of describing exactly how that is. Go check them out if you'd like to learn more. But for the context here, and so that people are on the same page, I'm going to actually work backwards in the sequence that's kind of shown on these figures. First, the raw data. So that figure there, this is what the ellipsometer actually measures. And what we're showing here is the x-axis is wavelength, and we're showing two lines, and they're psi and delta. And without going into too much detail, what these are telling us is the ellipsometer light beam is polarized, and we reflect it off of the sample, and in reflecting off of the sample, the polarization state changes. These lines both tell us how the sample changed the polarization state. I will leave it there. And then that's what we get. We get these two lines that tell us how the polarization state changed, but that's not film thickness, which is what we're interested in. So how do we get to the film thickness? And to do that, we have to fit an optical model to the raw data that we collected. And so I'm showing a schematic of a really basic optical model in the middle here. And there's really two main components that go into optical models. You have the optical properties, which are N and K. That's the index of refraction and the extinction coefficient. And those are material specific. They're basically like a fingerprint that describe how that material affects light, how fast the light travels in it, and how much that material absorbs the light. And then we also have the thickness of any layers that are present. And so basically, in the most simple example, let's assume that we know what the optical properties for these materials are, this blue layer and this pink layer, as I've shown them here. So we know those spectra on the right, and those feed into the model, and we just don't know the thickness. And using these optical properties and hypothetical thicknesses for the layer, we can simulate what would the polarization changes that we would measure be. And so in the base case where we know the optical properties and we just want thickness, we just simulate a whole bunch of different thicknesses. We run a fit regression on that. And once the simulated data, so on the raw data graph, the dotted black line, once that matches up to the raw data that we measured, whatever the corresponding thickness that was required to get that is, we take that to be the correct thickness. That's how it works. I'm going to talk about on the next slides pretty much a bunch of the different considerations that go into using ellipsometry to measure film thickness. So we're going to talk about all the different kind of ranges that you can run into: very thin films, very thick films, the case where the films are actually absorbing. Thought I said that you couldn't do that, but actually you can in some cases. We'll talk about the considerations there. And then also multi-layer stacks. So let's go to the next slide and we'll talk about this. This is a slide that I added because I wanted to give kind of hopefully an intuitive understanding of how the raw data that we collect actually gives you sensitivity to the thickness. And so what I did is I took a really simple case. This is a silicon substrate and it has a silicon dioxide layer on top. And I just simulated what's the raw data that the ellipsometer is going to measure for a whole bunch of different thicknesses of the silicon dioxide, this whole sequence. So on the upper left-hand corner, you can see 0 nanometers. That means there is no film. That's just what would we measure if it was bare silicon. And then right next to that, you see we have a 2 nanometer silicon dioxide film. And if you noticed, the raw data is almost exactly the same. Looks very similar, but you can see it's just tweaked down a little bit. It's just adjusted from the case where there's no film slightly. And that's basically what we're measuring in the case of very thin films. It's just little offsets in the data. And then we keep going to 5 nanometers, 20 nanometers, 25, on and on. And you can see, particularly on the left side at the short wavelengths in all of these spectra, you can see the emergence of these oscillations in the data, basically wiggles. And so you can see as we add more and more thickness, we get thicker and thicker, these wiggles are starting to pile up. And then we go through 150, 300, 500, 1 micron, 2 micron, and these wiggles start bunching together. And so effectively, you can kind of intuitively get an understanding here that basically, if we're able to fit kind of how fit this data and then fit how tightly bunched in the spectrum these wiggles are, we're getting information about how thick this film is. And you can see I've even zoomed in on the right for 5 microns. It can get really tight, and that starts to get into what gets tricky about measuring very thick films, which we will cover in a second. So we'll go to the next slide, Lyle. So I figured I would start with a nice basic vanilla happy case that works well. So here is a film. It's a silicon nitride film that is deposited on a silicon wafer, and it's a thickness of approximately 100 nanometers. And so this is a case, this is right in the meaty zone. This is where ellipsometry does really well. So we're showing on the left the model fit to the raw data that was collected by the ellipsometer. Everything fits really nicely. You can see there are some wiggles in the data. And then from that, we're able to determine the silicon nitride thickness. And then on the right, what I'm showing on the left is the example of one measurement spot. I'm giving an idea of how this can be expanded too. If we measure in multiple spots all over this entire wafer, we can do this fitting at each of those spots, and then we get a map of what the film thickness is over the entire wafer. So this is a really good case. Not a lot of limitations here. Works really well. That would be considered a bread and butter case of ellipsometry. So let's go to the next slide, Lyle. Now let's look at the case of really, really thin films. So I talked about this a little bit on one of the earlier slides. Here is an example of measuring a 2 nanometer film that's on a substrate. In this case, I've simulated silicon. And so you can see these are the 2 pieces of raw data, the psi and the delta, that ellipsometry measures. And so you can see in psi, the difference between the red line, which is the case where there is no film, And the black dotted line, which is the case where there is a 2 nanometer film, is very, very small. It's just different on the far left end of the spectrum there. Whereas if you look at delta, again, it is basically just a shift, but it is definitely measurable. And this gets to kind of some of the limitations for very thin films. In particular, psi gives us a lot of sensitivity to what the properties of that film are, in particular, the index of refraction of the film. And since there is almost no change for psi between there being a film and there not being a film, what this means is we have very little sensitivity to what the index of refraction of the film itself is. So in cases of really thin films, we often have to just make educated assumptions on what the properties of that film are. And then the other thing is it requires that the index of refraction of the film and the index of refraction of the substrate, they have to be sufficiently different. If they're really close to each other, then this shift that we're seeing in delta, which is what's giving us the sensitivity to the thickness, that will be minimized and will have very poor or no sensitivity to thickness. All right, so next on the next slide, we're going to talk about very thick films. So here on the other end of the spectrum where the wiggles are bunched very tightly together. And I'm showing an example here of simulating data for 2 different cases. These are the exact same film. They are it's 10 microns thick. But in the case of the red data, we've simulated the case where the film is perfectly homogeneous. It's very uniform. It's a nice high quality film where there's no differences throughout the top to bottom or left to right. And then in the case of the black dotted line, exactly the same thing, but we've just added 5% thickness non-uniformity, meaning that in the place we measured, the thickness of the film is actually varying a little bit. It's not perfectly flat. And you can see that the measured data is vastly different in the case of just adding a small amount of thickness non-uniformity. And the reason for this is basically because the path length through the material becomes very high when you have a pretty thick film. And so consequently, this means that the light has a lot of distance to be affected by the problems in the film, these non-uniformities, and they really affect the measured spectrum. So the thicker and thicker that films are, as you're trying to use ellipsometry to measure them, any little non-uniformities or issues with the film start to get magnified. And so ultimately, we need good quality films to be able to do really thick cases. Next slide, Lyle. All right, so this is the case of thin metal films. So I thought I said at the beginning we couldn't do metal films. They have to have transparency. It turns out if your metal film is thin enough, light can get somewhat through. So some of the light is absorbed, and then some of it is still transmitted through the film because it's not fully opaque yet. And those are cases that we can handle, but they can be kind of tricky. And so what I've shown here is simulated data for the case of multiple different thicknesses of a metal film. And so starting with yellow, that's the case of no film, then going through orange and then into purple and black. That's as the metal film is getting thicker and thicker. And you can see going from the case of 0 thickness up into about 50, 60 nanometer range, the spectrum is changing quite a bit. So we're getting sensitivity to the thickness and how it affects this measured data. But what happens is you kind of reach an asymptotic behavior here, whereas we get to even thicker, 60, 80, 100, these dark lines, they all start to become about the same. And that's basically the case where these films are getting thick enough that they are transitioning from partly transmitting to being fully opaque. And so that's the point where we lose the ability to measure the thickness of films. So it can only work where the metal is not fully absorbing. The other thing is we have to know or make logical assumptions about what the properties of the metal actually are, because if we need to be fitting both the optical properties, N and K, for the metal and the thickness, we can get strong coupling between those where we have an ambiguity and we can't say for sure if we got the right optical properties or the right thickness together. So that's another limitation. On to the next slide, Lyle. So the last case I'm going to cover here is the case of multi-layer film stacks. All the examples I showed before were for single films that were deposited on a substrate. In this case, this is an anti-reflection coating that we measured is deposited on glass, and it has a large number of films, 7 different layers present. And so on the left, we're showing the raw data and then the model fit. And you can see we're actually able to fit the shape quite well. And the key thing here is that this particular coating is actually just 2 different materials alternating. It's silicon dioxide and it's TiO2. And so what we've done is we've assumed that all silicon dioxide and all TiO2 layers have the exact same properties. And then what we're effectively doing is only fitting the thicknesses. And so this kind of gets at some of the limitations of what you can do with multi-layer film stacks. In this case, it works okay because we're fitting the individual thicknesses of the layers, and we've constrained the number of unknown layers that are present because there's really only 2 things. So in order to actually model this, we did have to know ahead of time how many of these alternating layers are even present. If this was a completely unknown multi-layer film stack, I would effectively be guessing on how many layers do we think they are and how, what could they possibly be. So this means that it requires some knowledge before we start of what's physically present there. We don't have to know with great accuracy what the thicknesses are, but we at least need to know the configuration of the layers. And then the other thing is, if this was the same film stack, but every single layer was a completely different material and we had to be fitting the optical properties for it, that would be asking too much, and there would simply be too much information for us to determine layer thicknesses accurately. All right, so back to you, Lyle.
Thanks, Max. So Max talked to you about what we can do with ellipsometry for films where light can get through. So what do we do if the film is completely opaque? The light can't make it through at all. And there's a lot of situations where this is the case. And so we have a number of techniques. These are really applicable with the case of metal films. And so we can measure films from a few nanometers all the way up to a few microns. We're going to talk mostly about X-ray reflectivity and X-ray fluorescence here, but there's also other measurements. For example, you could just measure electrical or magnetic properties of your films, and that can go up to even thicker samples. So like we discussed, many materials, particularly metals, can absorb light, and this limits the ability of optical methods to probe the thickness. However, for pretty much most of these materials over the relevant thickness range, they're somewhat transparent to X-rays. So we can use X-ray reflectivity or X-ray fluorescence, looking at specific elements to determine the thickness of the coatings. So I'll tell you a little bit about X-ray reflectivity. In some ways, there's some similarities with ellipsometry. So we're looking at the specular reflection of X-rays at shallow angles from about 0 to 8 or 10 degrees from the sample. And the interference between the thin layers in the film results in interference fringes. And these are very sensitive to the film thickness over a range of a few to maybe 200 nanometers. And I'll show you some plots like what Max showed. So this is really applicable to thin, smooth films. It gives you really high precision, accurate measurements of the thickness. And I'll talk to you about some of the limitations. So X-ray reflectivity gives you very good sensitivity starting at maybe 1 to 2 nanometers. Below that, it can be difficult to determine if you don't already know the density. But above that, you get very clear fringes, which are directly related to the thickness. And you don't necessarily need to know really anything about the film if there's just one layer. You can just use a Fourier transform of the fringe frequency to extract the thickness without a lot of modeling. Although typically you can use modeling because that allows you to also extract density and roughness. And another benefit here of X-ray reflectivity is that the models are quite simple. All you need to know is the density and the interfacial roughness, or you can fit those parameters as well for a few layers. And so you don't need to know the whole optical properties of the material. However, there are some limitations. One of the biggest ones is for thicker films, even just above 300 or 400 nanometers, you can barely see the fringes become really finely spaced. And I've even zoomed in that this angular range is much shorter here in the bottom left. And it becomes harder to resolve the fringes, and you need either higher resolution measurement, or in some cases, if the film is non-uniform, you simply won't see the fringes at all, and you're no longer able to measure the thickness. Another case where there's some limitations in XRR is rough films. So XRR works really well on very smooth films, like thin layers deposited on semiconductor wafers or coatings on glass. We can see here, this is a simulation for what would be a very nice case in the bottom center for a 50 nanometer thickness film, but just including 3 nanometer surface roughness, we can see that these fringes really rapidly decay. In this example, you could still fit the thickness, but you lose precision. There's not as many fringes. And if you have multiple layers, it'll become really difficult to extract all the properties because the fringes decay so quickly from the roughness. So another technique that's really widely used for characterizing optically opaque films is X-ray fluorescence. And we'll show an application on the next slide where we combine the X-ray reflectivity and the X-ray fluorescence together for measurement of an opaque film. So in this case, we irradiate the sample with X-rays, and then the specific elements in the film, particularly metals and heavier elements, will emit characteristic X-rays. And we can detect those X-rays as we measure the sample, and the intensity of those, in some cases relative to the substrate, can tell you the thickness of the film. This is really widely used, for example, in electroplated coatings, like electroplated metals, for printed circuit boards, and other applications. The challenge here is that you often can't directly model the data to extract the thickness, and many people rely on known standards, where you have a layer of the metal deposited on the same substrate, which you can directly use to calibrate the measurement. But some of the advantages here can work on much rougher films, much thicker films, up to a few microns, and it can typically be very fast or often use inexpensive equipment. So it's really widely used. So we'll show an application using a Rigaku Xtraya instrument. So this is a semiconductor tool that can map full 200 and 300 millimeter wafers. So in this case, we collected 49 locations across the wafer using both the X-ray reflectivity as well as the X-ray fluorescence. And we can generate a map of that thickness. And this is nominally a 25 nanometer thick titanium nitride film. So you can see in the top right, showing the edge in blue and the center in red, that there's a really obvious difference in the film thickness from that fringe frequency. And we can take all the points and model them and do the similar thing with the XRF, where you look at the intensity. However, here it's a bit harder to see. If you look closely, the peak labeled titanium is a little bit higher in the center than the edge because it's thicker in the center. And then we see the big peak from the silicon wafer characteristic X-rays. So like what Max showed, we can actually get insight into the variation by mapping using a small beam across many points on the wafer. In this case, you can see, as we expect, a really nice correlation between the XRF data, which here is qualitative since we don't have calibration standards, and then the quantitative XRR. And you can see that the wafer actually, this is quite a uniform coating. So even so we could see that really significant change in fringe frequency, it's actually a variation only about plus or minus half a nanometer across that full wafer. So we have really good ability to both map it and to have sensitivity to small changes in film thickness. And in this case, for a film that's strongly absorbing to light. So another example which Max talked about, and we'll have a couple other cases, is what if you don't know enough about the film? Either you don't know its optical properties or you don't know its structure. A lot of the techniques like X-ray reflectivity and ellipsometry require modeling to determine the thickness of individual layers. And so if you don't know about the film, for example, if you're reverse engineering or you bought this product and you want to figure it out, if you don't know ahead of time, then you have to use different techniques maybe to figure it out, or there are some techniques that don't require this. So I'll show kind of one interesting case, and then a few others are in the everything else bucket. So this is a really common application, for example, on semiconductor wafers like silicon, as well as metals like aluminum. They form a very thin so-called native oxide when exposed to air. And this is on the order of maybe a few angstroms to a couple nanometers thick. And while it is typically optically transparent, you can see through it on a piece of aluminum or silicon, we don't often have a good set of optical properties for modeling this. and it's very thin. And you might think that you could use the step height approach, just remove the oxide, but unfortunately, in most situations where we're handling these samples in air, the native oxide will just grow back before you can measure it. And so that will be a difficult approach. And in other cases, like if you're familiar with many metal surfaces, they're not polished like wafers, so we're not able to use X-ray reflectivity here. And for these oxides, they contain light elements, which aren't suitable for X-ray fluorescence, which is typically best on heavier elements that produce more X-rays. So we'll show you here a nice application using X-ray photoelectron spectroscopy to measure these layers. So a really quick intro. This probably won't teach you everything, but hopefully enough to understand the application. So XPS measures the binding energy of electrons in the sample. And these binding energies are sensitive to the local coordination environment. So if the metal is bound to another metal, or if it's bound to an oxygen, they're going to have a different binding energy. And these electrons that we're detecting have to escape from the film. And as the ones from the metal, which is under the oxide, escape, they get scattered by the oxide. And the amount that are scattered and that we don't see, we can use that ratio to determine how thick the film is, because for many of these oxides, that mean free path of the electrons is tabulated and available. So this technique is pretty specialized. It's limited to very, very thin films because you need these electrons to be able to escape, and they have pretty low energy, so like 5 to 8 nanometers. And it requires you to know the mean free path or to be able to simulate that. But this case works well in situations where not a lot of other tools can work. So we'll show just the really simple case of aluminum. So we see these two peaks, they're overlapping a little bit, so we have to fit them, but we see a nice contribution from the oxide. Those are the ones that can just directly escape. And then the buried metal, where a lot of them are scattered in the oxide. And using the relative ratio of those two, we can calculate the thickness. In this case, it's about 6.3 nanometers. And like ellipsometry, you can also map this over many points in the XPS if you're interested in variation. And this was just of a piece of commercial aluminum foil, so it's not polished or particularly smooth. So what do you do in other cases where you don't have good optical transparency, you can't expose the substrate, maybe you don't want to destroy the sample, or you didn't make it, or it's buried? And so there's some nice applications where how do you figure this out? And the answer that we typically use is kind of the gold standard. You just cut the thing in half and directly measure the thickness that you see once you've made a cross section. And this can be done in a number of ways. For example, it's really common to pot a piece of the sample in epoxy so it cures in this amount, and then you can grind and polish to expose the exact area where the film is that you want to see. Another thing we do often is using a focused ion beam to actually cut out a very small piece of the material and thin it down to tens of nanometers so you can actually see through it with electrons and use a transmission electron microscope. For soft materials, often you can use like something even as simple as a razor blade in the lab can make a decent cross section, or for certain materials, a microtome will work better. And so these apply to almost anything, but of course your sample is destroyed, you cut it in half. And the benefit is you can see all the layers in the sample in the region you're interested in, and you get direct pictures. So you don't need to know anything, there's no modeling, and you can just directly measure the thickness of all the layers, and you'll be able to see variation. So this is really widely used, but another limitation here is that you can't really practically map the thickness over a lot of areas. You'll have to just pick a few spots where you prepare the cross sections. So here we have this application of a cross section. In this case, it's a printed circuit board. So here, if we had just one of these layers, maybe that thin layer of nickel on copper, we could have approached this with X-ray fluorescence. But this becomes a challenge where we have a number of layers that are buried, and they're becoming very thick and have lots of heavy elements. And so here is a nice case where we can simply cut it in half, polish this cross section and look inside and directly measure the thickness. So we can see a layer of solder, about 100 microns with a layer, and then on top of a layer of copper. And in between them, we have a thinner layer of nickel. But the beauty of the cross section is you can actually see these kind of islands of this intermetallic phase that have formed. And you can see that actually varies from some locations where there's almost zero thickness to about 4 microns. So if you were using any sort of broad beam approach, you might miss that kind of inhomogeneity of those buried layers. So the cross-section really gives you the visibility. And once you're preparing these, you can get insight into other aspects of your material. For example, if there's other defects or heterogeneity, or even like the microstructure of the metals that your sample is made out of can also be exposed. And this applies not only to metals, but really any kind of material that you could polish or microtome, and you can see the difference. And if your films get into maybe the hundreds of nanometers range, then you could, instead of using an optical microscope like we did here, go into a scanning electron microscope. And that gives you different contrast as well. So certain materials might be easier to see the differences. So the next example is one that Max already showed in the ellipsometry example. This is the case. This is a camera filter with an anti-reflection coating. And so we started this project and we actually didn't know what the components are, so what materials were used to make the coating, as well as how many layers we had. So starting from there, we'd simply be guessing at that. So using ellipsometry or X-ray reflectivity to model this would be really hard without knowing the details. And this sample is way too thin to just look at with an optical microscope. So we prepared a TEM sample using a focused ion beam, and then you can really clearly see all the individual layers and count them, including a really thin little aluminum oxide layer. And in the TEM, we also have elemental sensitivity using energy dispersive X-ray spectroscopy, which is similar to X-ray fluorescence. So you can map different elements and determine the composition of the film. So in this case, we can see the alternating silicon-rich layers, which are the silicon dioxide, and then the titanium-rich titanium dioxide layers, and they're all on top of that glass substrate. So using this data, we can build the model for ellipsometry, but also in this case, we can just directly read off the thicknesses from these layers by measuring through like a line profile on the image. And then we also get insight into, for example, like the interfacial roughness and any defects and the nanostructure of the coatings. In this case, everything is amorphous without a lot of crystalline structure, so we don't see much, but in many cases, you can get a lot of insight into the different materials in the coating. All right, I hope that was a useful kind of summary into how we approach different film thickness when you know different amounts and have different materials. Wanted to thank everyone, and then we will get to our Q&A, and I'll hand it back to Carissa.
Perfect. Thank you, Lyle. And thank you, Dr. Junda and Dr. Gordon, for putting together such an informative overview on thin film measurements. Some really important details shared there. Now I have a few final housekeeping notes on the next slide before we get started with the Q&A. If you're interested in discussing any techniques reviewed today or need help with the current project, we do offer free discovery consultations with our covalent experts. You can schedule your appointment through the link sent in the chat now. On the next slide, please, you'll find information on how to access today's presentation. All materials will be uploaded to academy.covalentmetrology.com after we conclude. Last but definitely not least, you'll see a poll popping up on your screen here. If you could quickly answer these questions, it really helps us put better content, more effective content out for you guys each week. And now we can move to the next slide to get started on the Q&A.
Cool. Thanks, Carissa. Yeah, so we have some great questions that have been submitted by some of our attendees. So we'll go through them and give some of our thoughts and feedback. I think I'll kind of alternate a little bit through the techniques so that we can kind of cover multiple things. I'll start with the first one though, which is the question is basically, if you have a thick sample, say about 100 nanometers, and you still want to have information on the first few tens of nanometers of that film. Can you do that? And this was in reference to ellipsometry, I believe. And the answer, generally speaking, is yes. This is a little bit more of a complicated case, but in the case that you have a film and the material at the top of the film, so like top 10 nanometers or so, is different than the material at the bottom. The key takeaway here is that the raw data that we measure with ellipsometry will almost certainly be different than the data that we'd measure if the full 100 nanometers was homogeneous. And anytime the raw data is different, that means that there is signal there, that we have detected the change. And it's just a matter of whether we can create an optical model that is then able to reproduce what we've measured to actually determine what the properties of that top, material is. A good kind of example case here that we've handled in multiple situations is depth grading, which basically means that as you go down through the thickness of one film, although the film might actually be one material, say, like let's say it's some kind of a polymer, the properties, if you actually took each little slices along the way, are actually changing. So it might be absorbing a different amount of light, or the index of refraction might be changing. And so we have multiple methods of kind of modeling these changes with depth. So that sounds like that would probably be the type of thing that would apply here. The alternate case too is if you measure a film and it seems identical to another film that is homogeneous, then that's usually good evidence for the fact that it is in fact a homogeneous film. So I hope that adds some context to that question. Lyle, I guess we'll go to one for you. Just how about really just a quick clarification on just the XRR graphs? Can you go into what the y-axis is? What's shown there on the data where we see the fringes?
Sure. The y-axis is basically the intensity of the reflection. So the counts, in that case, it's counts per second. So how many X-rays are reflected. And it's over X-ray reflectivity. The reflection drops over many orders of magnitude as you go from like almost grazing near the critical angle to higher angles. So that's plotted on a log scale. So that intensity is usually like maybe 4 to 7 orders of magnitude. From some samples reflect almost all the X-rays, and then it drops to just a few counts where there's like 7 orders of magnitude less reflection.
Great. Yeah, thanks. Real quick, this is a kind of a quick, I hope, question and answer. How rough is the surface roughness related to using an ellipsometer? So how much roughness can be present in a film and we still use an ellipsometer? There's actually kind of two things here. In creating optical models for our films, we can often add a separate surface roughness layer, which is detecting the effects of the surface roughness. So in that sense, in a very crude way, you can actually use ellipsometry to measure surface roughness. It's nowhere near as good as pretty much all profilometry techniques. That being said, that can be done. However, that's usually limited to surface roughnesses that are on the order of maybe tens of nanometers. Once you start to exceed that value, basically the easiest way to think about it is what you get into a regime where the surface topography, the features are actually the size of them is starting to approach the wavelength of light that you're measuring. So now you're in a situation where you're actually starting to enter a scattering regime. The films with roughness that are 100 nanometers or more can actually be measured with ellipsometry. We will not be able to actually model what the roughness thickness is in those cases, but we can still collect data. And although the analysis is a little bit more complicated sometimes, and there are caveats to the results that we get, useful information can still be determined from quite rough films, multiple hundreds of nanometers of roughness. All right, Lyle, we'll go back to you. Sorry, let me hard to answer the questions and then find the next ones.
There's a good XPS question I see.
Sure. Yeah. Why don't you grab
that one?
Yeah.
Yeah. Someone is asking about measuring thickness of thin films by XPS, and they're also interested if you can also do it by sputtering surface layers. This is something we didn't really talk about, so a nice segue into that. But yes, you can measure films either using XPS or other sputtering techniques like TOF sims, where you incrementally remove the film by etching or sputtering, typically with like argon atoms. And then you can remove surface layers. And if you've calibrated that sputtering rate, then you can accurately measure the thickness of surface layers. And we do that routinely using XPS.
Cool. Yeah. Thank you, Lyle.
I can answer another XRR question because I see it.
Sure.
There's a question, can XRR measure on films where, or does it require the substrate to be opaque compared to the film? And the answer is no. You can do freestanding films if you wanted. That's not typically that common, but many cases we have really heavy metal films, like we look at like iridium X-ray mirrors on top of silicon substrates. So there the film is much more absorbing than the substrate. And those cases actually work very well. You just need contrast. It doesn't matter which way it is.
Sure. Okay. I'm going to grab another question related to ellipsometry. If you have a multi-layer stack of an optically transparent film, and you know the composition and thicknesses of the 4 to 5 underlayers, and those are somewhere in the 10 to 500 nanometer range, what's the best method to determine the thickness of a very thin, say 1 to 5 nanometer layer that is also transparent, and find that material's NNK values, the optical properties of that material? So I'm going to assume that basically means we have a multi-layer stack, and we basically know all the information about those underlayers, and there's a thin surface layer, and we want to determine properties for that. In principle, that is doable. However, the key thing is that, as I showed with the examples of increasing film thickness and how the spectrum becomes dominated by a lot of what I'll call wiggles, in order to measure the properties of a very thin film that's on top of a multi-layer, and particularly if some of those layers can be pretty thick relative to the surface film, we are going to need to be able to have a very accurate optical model. So that will demand that we are able to model all the layers below with very high accuracy. And the reason why is that, let's say that our optical model is not able to super accurately model what is underneath this thin surface layer of interest. There's going to be some mismatch between what we've modeled and what we've measured. And the problem is, we know that a very thin surface layer is just going to induce a small shift in the measured spectrum. And so what that means is the sensitivity of our model while fitting to the measured data is going to be dominated by what it's missing in terms of modeling the lower layers than actually what is caused by the surface layer. So the quick version, or the quick answer is that is doable, but it requires really good optical modeling of the layers that you have below the surface layer.
Right. I see a couple of questions. There's an interesting one. Someone's asking, how do you measure the thickness and uniformity of the coating around a spherical object. Without knowing too many details, I think this would be in the case of cross-section. We would just cut it in half and measure the thickness, and it would give you kind of one plane. And that would work. If there's really small spherical, like nanoparticles, in some cases, XPS can get you coating thickness as well. And then there's another question on metal plating. So we talked about this a little bit with X-ray fluorescence. So for like flat-ish objects, this is something we can do with X-ray fluorescence. It helps if you have the right standard. And then they also ask, what about metal plating on different shaped objects, like, for example, a screw? In this case, a cross-section can work well, or you can also use some electrochemical techniques where you actually etch off or dissolve the metal, and you can measure the thickness that way. And so there's a few different approaches that can work well, from flat objects to like weirdly shaped things like screws with threads.
Cool. Thanks, Lyle. Here's another actually really kind of interesting and insightful question. In ellipsometry, is the surface roughness induced scattering? So this is what I talked about before. As the surface gets kind of rough, hundreds of nanometers of roughness, and you have scattering. Is that scattering sort of incorporated into the derived K values, the absorption in the material, since scattering effectively increases the extinction? That's actually a great question. The answer is no. And the reason why is that ellipsometry is a technique that is based on ratios of the polarization, not the intensity of the light that's measured. So we are determining both N and K from the ratio of how different polarization states are affected by the material. Whereas what happens when you have the scattering from the surface is that the intensity of the beam, so how bright it is when it reaches the detector, that is decreased. However, that actually should be relatively independent of this polarization ratio, which is what we're measuring. This is different from the case where if you measure transmission intensity through the film. In that case, scattering definitely affects the intensity of what you would measure. And if in the case of specular transmission, so just undeviated path for the beam, scattering and absorption will both look like the same thing because they'll look like decreased measurement beam intensity. So that's a kind of an interesting question.
Right. There's another good question. I hope I interpret it correctly. They're asking, what's the spatial resolution for the non-real space techniques? So I hope this is asking about like for XRR, XRF, and ellipsometry, where we showed examples mapping across a wafer. We didn't really talk about the spatial resolution for those techniques. So like how fine features can you map? So for our instruments, for all those techniques, the beam can be focused down to a few hundred, like around 300 or slightly below microns. So that gives you an idea of the spatial resolution. And then there are some instruments that can go smaller. And then in certain cases, like if you're using SEM, EDS, you can go to around a micron. So hopefully that answers the question.
Would you like to have a little bit of an interactive answer, Lyle? How about this one? Out of everything that we have, what would we say is the best methodology to measure DLC, which I'm interpreting as diamond-like carbon, thickness of around 2 nanometers?
I think we don't know the substrate or the shape or roughness. X-ray reflectivity definitely works in those cases. And I'm assuming ellipsometry probably works too.
Yeah, that's my thinking. Ellipsometry could work. I think there's a couple things you could do here. Obviously, if you had a step height that was created, you could use AFM. But probably one of the optical methods would be best. Obviously, substrate dependent.
Yeah, and then if that was coated on a rough object or like weird shape, like often those are used for wear-resistant coatings, then something like TEM might be necessary, but could be tricky where the roughness might be greater than the film thickness. That can be a challenging application.
All right, I'm going to take actually just two questions that are somewhat related, and they're getting the same thing. And it's basically talking about what are the requirements and what do you need to measure really thin coatings. In particular, one of these questions is about relatively transparent coatings on sapphire wafers. And the key thing in that case is the best case or best way to do this with at least ellipsometry is it's best to measure your substrate. In this case, sapphire is a pretty well-known material, but in all instances, it's nicest if you can measure your substrate, so a piece of sapphire, preferably from the same batch, that has no coating, and then your coated sample, so that in each situation, you're only dealing with a very limited number of unknowns for building your optical model. And then actually, I'll do one more that is pretty interesting as well. And it's basically for thin films in which the optical properties of the coating are very similar to the substrate. Do you need to know what do you need to do to be able to handle that situation, basically? And is that even possible? And the answer is yes. What happens is we get thickness information from the wiggles in the data, and the amplitude of those wiggles gets smaller and smaller as the optical properties, the index of your film, gets closer and closer to the substrate. The case where those wiggles are completely extinguished only happens where there's very, very good index match between your film and your substrate. So there's almost always very weak wiggles, interference oscillations that can be used to determine thickness for coatings on films, even when they're close. But it does, in order to have thickness sensitivity, it does require that there is at least a little bit of a difference. And by that, it's depends a little bit on thickness, but probably into the second decimal place in index. That being said, if you're trying to measure the optical properties of the coatings, which is not really the question, but just as a little aside, if it turns out that you see absolutely no interference oscillations, that actually still allows you to kind of get pretty good information about the optical properties of the coating, because you know they must be so similar to your substrate in order to produce that condition. So any other questions, Lyle, on here that are worthwhile, or have we reached the limit?
I think we might have gotten to all of them.
All right, great.
Perfect. Well, it's time to wrap up. Thank you again, Dr. Gordon and Dr. Jinda, and thank you all for joining us today. We really appreciate you spending your time with us. We have these talks once a month, so monitor your email for upcoming topic registrations. Thank you and have a great day.